Alright, in this video I'm going to do a sample problem involving just a very basic conservation of energy equation. So let's say that I'm standing on top of a cliff and I have a ball and I want to drop it to the bottom. Okay, the cliff is 100 meters tall, the ball is 10 kilograms, and I've written here I want to figure out the velocities at different points, but I'm going to start by talking about the energy at different points. So right here at the top, I have done some work in order to lift this object up to the top of this cliff. And so I have therefore stored energy in that object that is gravitational potential energy. And remember that gravitational potential energy at any instant is equal to mg times the height above the relatively lowest position. It doesn't always necessarily have to be the ground. So if we wanted to calculate that, we're just taking 10 times 100 times 10. So I actually get 1 times 10 to the fourth, or 10,000 joules. Now up at the very top, where the object is not moving at all and it's still resting in my hand, all of the energy is gravitational potential energy. So here, the kinetic energy would be 0 joules. Now, if I dropped that object, we know that it's going to start falling towards the ground. It's going to start accelerating due to gravity, so it's going to go faster and faster and faster. And the lower it gets, the less gravitational potential energy it has and the more kinetic energy it has. So essentially it's like a balance. As kinetic energy goes up, gravitational potential energy goes down, and there's a direct conversion from one to another. Remember, we're assuming a closed system, so we're not dealing with any heat loss due to friction or air resistance or anything. So we know that if we drop the ball down all the way to the bottom, here, where the height is now 0, I will have 0 joules of gravitational potential energy. And that means all of that energy has become kinetic energy. So at the bottom, we know right before it strikes the ground, it's going to have 1 times 10 to the fourth joules of kinetic energy. Now, if we look at the point where we're just halfway down, here we'd say, well, it's split 50-50. It's lost half its gravitational potential energy, so that means half of it must have gone to kinetic energy. So here at the halfway point, I would say that my GPE is 0.5 times 10 to the fourth, or 5,000 joules. And that means that my kinetic energy there at that point then is 5,000 joules. All right? So in order to figure out my velocities, this is very easy. So I've already done the joule conversion, but it obviously, or honestly, a lot of times you're given a problem where you're trying to figure out the velocity at the bottom and you're given the height. So we know that all of your gravitational potential energy has completely converted to kinetic energy. So let's just set up a problem where we see that conservation of energy. We know that GPE at the beginning is going to be equal to kinetic energy at the very end. So I'm just going to plug in, and I'm going to use my equations this time instead of just using my numbers. So let's see if we can figure out what the velocity at the bottom is. So we have that mgh equals 1/2 mv squared. And so if I were to cancel my m's, then I just get gh equals 1/2 v squared. So 10 times 100 equals 1/2 the velocity squared. So that would be 1,000 times 2. So let's just look at things. I can't do the square root of that. So 10 times 1,000 divided by 0.5, and then second square root, second answer, I get 44.7 meters per second. So the final velocity right here would be 44.7 meters per second. Now, up at the very top, we know that there's no kinetic energy, so the velocity here must be 0 meters per second. But we also could figure out the velocity here now. We know there's 5,000 joules, so we're just going to set 5,000 equal to 1/2 mv squared. We could also set mgh equal to 1/2 mv squared here and use the height as 50 meters. Either way, we would get the correct answer. Okay, so 5,000 equals 1/2 of 10, so that'd be 5 Okay, so we just have to take the square root of 1,000, which is 31.6. So right here, we're going 31.6 meters per second. So again, using conservation of energy makes it very simple. We don't have to use our constant acceleration equations anymore to solve for these velocities. It's a lot easier using energy. So this is a problem where we're dropping something straight down. Now, if I were to have a problem like an inclined plane problem, remember how hard those inclined plane problems were when we had to use like g sine of theta and all that mess? Well, now, if we're dealing with no friction, we can just use this as our height. And if I were to allow a box to slide all the way down, let's say this is 10 meters, all the way down here, I could find the velocity at the bottom of the incline by just setting the gravitational potential energy at the top is equivalent to the kinetic energy at the bottom and use the y component of the height. Okay. All right, so that's just a very simple example. You'll be applying in a little bit more complicated examples, but don't overthink it. Really, we're just dealing with the idea that we're converting from one type to another. So it's just a tipping balance. If gravitational potential energy is lost, then that is equivalent to the kinetic energy that is gained.